These are some of the final images taken by Cassini. Just a few of the 450,000 pictures that the spacecraft has captured in the past 13 years.
Cassini's final dive into Saturn was supposed to be perfect. Every movement was calculated, every transmission expected, and every reading meant to close the mission cleanly. But years later, when scientists reanalyzed those final transmissions, they found gaps in the data stream.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
SOI burn attitude or pointing position, and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe.
Strange readings that didn't align the way they should have. Now, those last few seconds are being re-examined for one reason. They contain data that doesn't fit any current model of Saturn.
Thanks to Cassini, scientists have learned invaluable information about Saturn and its rings, namely the discovery of an ocean on the moon Enceladus.
A clean mission. By the time Cassini-Huygens reached its final year in 2017, there was very little left to prove. The spacecraft had already spent over a decade orbiting Saturn, mapping its rings, studying its moons, and sending back an enormous volume of data that reshaped what scientists understood about the outer solar system.
After everybody started getting their science, the beauty of what I saw in Cassini was they started collaborating with each other.
It had revealed methane lakes on Titan, water plumes erupting from Enceladus, and storms on Saturn that dwarfed anything seen on Earth. From a scientific standpoint, the mission was already complete. But instead of simply shutting the spacecraft down, engineers made a decision that would define Cassini's legacy. They would send it into Saturn. This final phase of the mission was called the Grand Finale, a series of 22 orbits that would take Cassini closer to Saturn than any spacecraft had ever gone before. Instead of remaining at a safe distance, Cassini would dive repeatedly between the planet and its rings, entering a region that had never been directly studied. No one knew exactly what Cassini would encounter in that gap. The space between Saturn and its rings could have contained dense particle fields, capable of damaging or destroying the spacecraft. Even small fragments moving at orbital speeds could have been enough to disable its instruments. But the potential reward outweighed the risk. For the first time, scientists would be able to measure Saturn's gravity, magnetic field, and atmospheric properties.
Instead, the magnetic field was curving around the moon.
At extremely close range, instead of observing from afar, Cassini would move through regions where the planet's internal structure could be studied more directly. It would get as close as possible, and then it would end. The decision to destroy Cassini was not symbolic, it was necessary. Some of Saturn's moons, particularly Enceladus, showed strong evidence of subsurface oceans that could potentially support microbial life. If Cassini were left drifting in the system, there was a risk it could eventually collide with one of these moons and contaminate it with Earth-based microbes. So the mission ended the only way it safely could. Cassini would burn up in Saturn's atmosphere. On September 15, 2017, the spacecraft made its final descent. As it entered the upper atmosphere, it continued transmitting data back to Earth in real time. Sensors measured temperature, pressure, and atmospheric composition while the spacecraft began to experience increasing drag. For a brief period, everything worked exactly as planned. Cassini continued sending data even as the atmosphere began to tear it apart. Then, as expected, the signal stopped. At that moment, the mission was considered complete. Everything Cassini had recorded during those final passes was transmitted back to Earth. Engineers archived the data. Scientists began analyzing it.
There were also unexpected signs of ionized water vapor molecules.
It was assumed that the most important discoveries had already been made during its operational lifetime. The final moments were seen as a conclusion. But there was one detail that did not stand out at the time. During the grand finale orbits, Cassini was moving through a region of Saturn that had never been directly measured before. Its instruments were collecting data under conditions they had not been designed to handle at that level of proximity. At the time, nothing in those final transmissions appeared significant enough to change the understanding of Saturn. The data was processed, cataloged, and added to the massive archive Cassini had already produced.
The surface and the normal wavelengths that our eyes would use, and the radar operates by making images in narrow strips.
But years later, as scientists returned to that data with better tools and better models, something began to stand out. Data line up. In the months after Cassini-Huygens ended, the focus shifted from exploration to analysis. Cassini had returned an enormous volume of data over its 13-year mission, and the final orbits alone produced some of the most detailed measurements ever recorded around Saturn. Teams across different research groups began working through this information, separating it into categories, calibrating instruments, and comparing results against existing models of how the planet was supposed to behave. At first, everything followed a familiar pattern. Some measurements confirmed what scientists already suspected. Others refined existing models. But scattered within those data sets were small inconsistencies that did not immediately stand out as major discoveries. They were subtle, easy to overlook, and often attributed to the extreme conditions under which the data had been collected. Cassini's final dives were not clean observations. They were taken at speeds and distances where instruments were being pushed close to their operational limits. That meant noise in the data was expected. Slight distortions, irregular readings, and unexpected spikes were all considered normal under those circumstances. So when certain measurements didn't align perfectly, they were not treated as anomalies. They were treated as limitations. One of the first areas where this became noticeable was in Cassini's gravity measurements. By tracking tiny changes in the spacecraft's velocity during its close passes, scientists could map Saturn's internal mass distribution. The expectation was that the data would fit within known models of how gas giants are structured. But some of the results suggested something more complicated. Instead of behaving like a planet with clearly defined internal layers, Saturn appeared to have a diffuse interior where heavier elements were not concentrated neatly at the core, but spread outward into the surrounding regions. This wasn't entirely impossible, but it introduced uncertainties into models that had previously been considered reliable. At the same time, Cassini's instruments were measuring Saturn's ring mass with unprecedented accuracy. For years, scientists had debated how massive the rings actually were, because that value helps determine their age. Younger rings would be brighter and more massive, while older ones would be darker and thinner due to gradual erosion. The final measurement suggested that Saturn's rings were much less massive than expected. That implied they might be younger than previously thought, but that created another problem. If the rings were relatively young, then something must have formed them in the recent past, and there was no clear evidence of an event large enough to explain their origin. Meanwhile, another set of data focused on the interaction between Saturn and its rings revealed a process known as ring rain, where charged particles from the rings are pulled into the planet's atmosphere by magnetic forces. Cassini detected this phenomenon in detail, showing that material from the rings was slowly falling into Saturn over time. All of these findings were important, but none of them immediately pointed to anything extraordinary. They simply made Saturn more complex than expected. And then there was the magnetic field. Cassini had been measuring Saturn's magnetic field for years, but the final orbits provided the most precise data ever recorded. The expectation was that, like every other planet, Saturn's magnetic field would be slightly tilted relative to its rotational axis. But the data showed something unusual. Saturn's magnetic field appeared to be almost perfectly aligned with its rotation. That might sound like a minor detail, but it presented a serious problem. According to existing theories, a perfectly symmetrical magnetic field, there should be at least a small tilt caused by internal motion within the planet, but Cassini didn't detect one. At first, this was treated as an oddity, but over time, as more data was reanalyzed and compared, a pattern began to emerge. The closer it got. As researchers continued working through the final datasets from Cassini-Huygens, something subtle began to change in the way the data was being interpreted. Early on, most of the irregularities were treated as isolated issues. Each one had a possible explanation on its own. But when those measurements were placed side by side, they started to overlap. The deeper scientists looked, the harder it became to treat these inconsistencies as separate events. They were not just appearing in one system. They were showing up across multiple instruments, measuring completely different aspects of Saturn at the same time. Cassini was not just detecting noise, it was detecting complexity. One of the clearest examples came from the region between Saturn and its rings, the same gap Cassini repeatedly passed through during its final orbits. This area had never been directly sampled before, and scientists initially expected it to be relatively empty, a space largely cleared by gravitational forces. Cassini detected unexpected particle activity, including fine dust and charged material moving in ways that did not fully match predictions. Some of these particles appeared to be influenced not just by gravity, but by electromagnetic interactions that were stronger and more dynamic than expected at that distance. At the same time, Cassini's instruments were recording changes in plasma density around the planet. Plasma, a state of matter made of charged particles, is heavily influenced by magnetic fields. The expectation was that plasma behavior near Saturn would follow relatively stable patterns shaped by the planet's magnetosphere. Instead, the readings showed variability. Regions that should have had consistent plasma densities were fluctuating. Some areas showed sudden increases, while others dropped unexpectedly. These changes were not random enough to be dismissed, but not consistent enough to form a clear pattern. And then there were the radio emissions. Saturn produces natural radio waves that can be detected by spacecraft, and these emissions are often used to study the planet's rotation and magnetic field. Cassini had been monitoring these signals for years, and scientists expected them to behave in predictable cycles. But during the final orbits, the signals became harder to interpret. The frequencies shifted in ways that did not align cleanly with Saturn's known rotation rate. In some cases, the signals suggested multiple rotational influences, as if different layers of the planet were not moving in perfect synchronization. That alone would have been unusual, but combined with the magnetic field anomaly, it created a deeper issue. If Saturn's magnetic field was nearly perfectly aligned, and its radio emissions were not matching a single rotation rate, then something about the planet's internal dynamics was not behaving the way existing models predicted. And none of these observations existed in isolation. They were all happening in the same region, during the same phase of the mission, at the closest distances Cassini had ever reached. The environment around Saturn was not behaving like a simple system governed by a few predictable forces. It was behaving like a system with overlapping influences. Gravity interacting with electromagnetic forces, plasma responding to shifting magnetic conditions, particles moving through regions that were not as empty or stable as expected. Each layer added complexity, and the more layers scientists uncovered, the harder it became to simplify what Cassini had observed. Because what was once thought to be a relatively well-understood planet was starting to look far more complicated. Too perfect. Out of everything Cassini-Huygens measured during its final orbits, one result stood out more than any other, not because it was dramatic, but because it was too precise. For decades, scientists have studied planetary magnetic fields to understand what is happening deep inside a planet. These fields are generated by the movement of electrically conductive material in a planet's interior, usually in a liquid core. Because that motion is turbulent and uneven, magnetic fields are almost never perfectly aligned with a planet's rotation. Earth's magnetic field, for example, is tilted. Jupiter's is tilted. Every planet with a measurable magnetic field shows some level of asymmetry, except Saturn. Cassini's final data showed that Saturn's magnetic field is aligned with its rotational axis to an almost exact degree. Because according to the physics of planetary dynamos, a magnetic field that is symmetrical should not exist. In order for a magnetic field to sustain itself, there needs to be some level of irregular motion inside the planet. That irregularity creates variations that maintain the field over time. Without it, the system should weaken or collapse. But Saturn's field does not behave that way. It is almost perfectly symmetrical. This creates a contradiction. The internal motion required to generate the field should introduce asymmetry, but the measurements show almost none. That means either the internal structure of Saturn is very different from what scientists expect, or the processes generating its magnetic field are not being fully understood. and Cassini made this contradiction harder to ignore. During the grand finale, the spacecraft passed closer to Saturn than ever before, collecting the most accurate magnetic field data in the mission's history. If there had been even a small tilt, even a fraction of a degree, Cassini should have detected it. That alone would have been enough to challenge existing models. But when combined with the other irregularities, the fluctuating plasma, the shifting radio signals, the unexpected particle behavior, it became something else. It became a pattern of uncertainty. Because if Saturn's magnetic field is not behaving the way it should, then it affects everything around it. The magnetosphere shapes how charged particles move, how radiation is distributed, and how energy flows through the space surrounding the planet. It influences the entire system, and if that system is not fully understood, then the data collected within it becomes harder to interpret. Cassini did not just collect strange readings. It collected readings from a system that may not behave according to the assumptions used to analyze it, which means some of what we think we understand about Saturn could be incomplete. Cassini's last moments were not just about sending data. They were about sending data from the most extreme conditions the spacecraft ever experienced, conditions where the known models were already starting to fail. And in those final moments, something else happened. Something that has made those last transmissions far more difficult to fully explain. The final data gap. By the time Cassini-Huygens entered Saturn's upper atmosphere on September 15, 2017, everything about the sequence had been carefully planned. The spacecraft would maintain communication with Earth for as long as possible, transmitting real-time measurements as it descended, until the increasing atmospheric pressure caused it to lose stability and burn up. This part was expected. What mattered most was not the destruction, but the data collected in those final minutes. Cassini's instruments were still active as it crossed into regions no spacecraft had ever measured directly. It was recording changes in atmospheric density, temperature gradients, and chemical composition, while simultaneously transmitting that information back to Earth at the speed of light. For a brief period, everything worked exactly as designed. Engineers tracked the transmission in real time, knowing that every second counted, and then, as expected, the signal ended. At the time, that moment was treated as a clean cutoff. The spacecraft had reached the point where it could no longer maintain orientation. Its antenna could no longer stay locked onto Earth, and communication was lost. That was the official explanation, and it aligned with the mission design. But when scientists later revisited the final transmission logs in detail, they noticed something subtle. The data did not end in a perfectly continuous sequence. There were gaps not large enough to suggest a major failure, but noticeable when the data was reconstructed at high resolution. Certain measurements appeared slightly out of sequence. Some packets were incomplete. Others contained values that were harder to reconcile with the surrounding data. At first, this was attributed to the conditions of the descent. As Cassini entered Saturn's atmosphere, turbulence would have affected its orientation. The increasing drag would have caused slight instability. Communication signals could have weakened or fluctuated. As the spacecraft lost control, all of that made sense. But the deeper researchers looked, the less clean the explanation became. Because the inconsistencies were not random. They appeared in specific parts of the data stream, particularly in measurements related to plasma interactions and electromagnetic readings. These were the same systems that had already shown irregular behavior during the earlier grand finale orbits, which meant the final gaps were not just about signal loss. They were tied to the same part of the environment that had already proven difficult to model. This created an important question. Were these gaps simply the result of a spacecraft failing under extreme conditions? Or were they the result of measuring something that was not behaving in a predictable way? There is no evidence of anything dramatic or external interfering with Cassini. No indication of artificial signals, no hidden messages, no unknown structures. The data remains grounded in physics. But the physics itself becomes harder to interpret at that level, because Cassini was operating at the edge of its capabilities, in an environment where multiple forces, gravity, magnetism, plasma, and atmospheric dynamics were interacting at once. And when too many variables overlap, even accurate measurements can appear incomplete. A dataset that answers many questions but leaves a few open. And those unanswered parts all point in the same direction. The closer we got to Saturn, the less complete our understanding became. Closer, but not clearer. What makes Cassini's final moments unsettling isn't what the spacecraft found. It's how close it got, and how much still didn't make sense. Cassini-Huygens didn't observe Saturn from a distance. It moved through regions no spacecraft had ever entered, collecting the most direct measurements we've ever had of the planet's structure, its magnetic field, and the space between it and its rings. And yet, even at that distance, the data didn't fully resolve. Exploration is supposed to reduce uncertainty. Every mission is meant to replace questions with answers. Cassini did that for years. It explained Saturn's moons, its rings, and its atmosphere in ways no one thought possible. But in its final moments, the pattern shifted. Instead of simplifying what we knew, it exposed how much of it might still be incomplete. Cassini didn't just show us Saturn. It showed us the limit of how well we understand it. Because if the most precise measurements we've ever taken still don't fully fit the models we trust, then that leaves one question that Cassini never answered. Not what Saturn looks like, but what Saturn actually is.